The first step is to open the notebook in Google Colab. You can also run it in your local computer if you have a GPU. In this lecture, I will demonstrate the process using Visual Studio Code on my local computer. Let's open the script. We select the right kernel. I choose TFGPU environment. Section 0, install dependencies. Okay, the very first thing we do, install the libraries we need. Most of them are already in Anaconda or Colab. We only need some of them, such as Raster, Torch Info, Segmentation, Models, PyTorch. You'll see something about scrolling. That's normal. Just wait until you see all dependencies installed. If you see any red error about SSL, that's a Windows issue. It does not affect the libraries. Ignore it and continue. Now we have all dependencies installed in the output. Section 1, imports and device setup. Now let us import everything we need and check that our GPU is ready. I want you to notice something here. We set a random set number 42. This makes our results reproducible. Every time you run this notebook, you will get the same results. Without the set, the random numbers would be different every run. Let's run cell 1. Look at the output. It tells you your device, your GPU name, and how much memory you have. Device CUDA. CUDA means your GPU is active. If you see CPU here, stop and go to your environment settings to enable the GPU. Run 8.6. Can anyone see the GPU name in their output? What GPU do you have? Section 2, download and explore Eurostat dataset. You can download a Eurostat dataset, for example, from Zenodo. Download it and then unzip. For this lecture, we already downloaded it. Now we load our dataset. It is real Sentinel-2 satellite images from Europe. It has 27,000 image tiles across 10 plan cover class. Each tile is 64 by 64 pixel. For example, this one, forest. This is river, and so on. The path of our dataset. Let's run this cell. You can see 10 class printed here. Notice the number of tiles per class is different. This imbalance is important. We will deal with it later when we talk about those functions. Now let us visualize one tile from each class. Let's run cell2b. Look at this grid. 10 completely different landscapes. Forest is dark green. River is blue. Industrial has gray rooftops. Residential has regular street patterns. This is what our unit will learn to distinguish. Not just yes or no vegetation, but which specific land type every single pixel belongs to. Highway is one of the hardest classes. Can you see why? It is small, narrow, and looks similar to roads in residential areas. Our model will struggle here first, and we will see that in the results. Section 3, Segmentation Mask Concept. Before we build the model, I want to show you exactly what the output will look like, because this is the most important concept in the whole lecture. A segmentation mask is just a 2D array, same size as the image. Each number in the array is a class index. 0 means annual crop, 1 means forest, 8 means river. Now let's run cell 3 mask concept visualization. Look at these three images side by side. On the left, the original Sentinel-2 satellite image. In the middle, the integer mask. You can see numbers displayed as colors in the heat map. That grid in the middle, those are all the pixels we set to river class. Index number 8. On the right, the color code map. This is what a land cover map looks like. Green is forest, blue is river. This is exactly what our unit will produce after training. The model will look at the left image and output the right image automatically for every pixel. Pause here and look at the color map. Does it make sense to you? The river strip is blue. The rest is green for forest. This is what a trained model will produce, but automatically from a real satellite image. Section 4, Dataset class with a geographic split. Now we build the Dataset class. This is where I needed to tell you about the most common mistakes in geospatial machine learning. If you do this wrong, your results will look great in the notebook, but they will be completely wrong in the real world. The mistake, random shuffling before splitting. In normal machine learning, you shuffle your data and take 20% for validation. For satellite images, do not do this in machine learning or deep learning. Why? Because neighboring tiles share the same spectral characteristics. If you shuffle randomly, your validation tiles end up right next to your training tiles on the map. The model has basically already seen them. Your accuracy score will be 10 to 15 points higher than it should be. The fix is one line of code. We sort the file names, which keeps geographic order, and we slice the first 80% for training and last 20% for validation. Never shuffle before slicing. Let's run cell 4, create datasets and data loaders. Great. 21,600 training samples and 5,400 validation samples. Now, look at the batch inspection output. This is something I always do before training. 3 checks. First, the image shape. 64 batch. 3 channels, height and width. Second, the value range. It must be between 0 and 1. We divide by 255. This is correct. Third, the mask unique values. You should see all 10 class index from 0 to 9. If any of these 3 checks fails, stop. Do not train. Fix the data first. These 3 checks save you hours of debugging. A model that trains on unnormalized data or wrong class indices will produce garbage results that are very hard to diagnose. Section 5 Unit Architecture. Now we build the star of this lecture, the unit, from scratch in PyTorch. I want to take you through each piece one by one because understanding the architecture will help you modify it later. DoubleConv. Every single block in the unit uses the same pattern. The full unit. The unit has 3 parts. The encoder compresses the image. It learns what is in the image. The bottleneck is the deepest, most abstract representation. The decoder expands back to full resolution. It learns where each class is. The critical innovation is the skip connections. Before we pull, we save the feature map in the decoder, we paste it back in the matching level. This gives the decoder both global context and precise spatial detail. Skips.append x, which save here after conv before pull. Now let's run cell 5. Look at the output shape. 2 by 10 by 64 by 64. Batch of 2 images, 10 classes, 64 by 64 pixels. Every pixel gets a score for every class. That's our segmentation output. And about 31 million trainable parameters. That's a solid model, not too small, not too large for our GPU. If you change it in channels from 3 to 13, you could use all full 13-band Sentinel-2 data. The rest of the model stays exactly the same. That's Capstone Challenge 1. Section 6, Attention Unit. Now here is a powerful extension, the Attention Unit. Let's run cell 6A, build Attention Unit. You can see it has about 1% more parameters than the standard unit, a small cost for a significant quality improvement on difficult class. Cell 6B, Attention Map Visualizer, we run it after training. So we will come back to this after training. It will show you exactly where the model is paying attention. Bright areas, the model is focused there. Dark areas, suppressed. Very useful for understanding your model. Use attention unit when you have thin linear features, reverse roads, fill boundaries, or when class imbalance is severe. The standard unit is fine to start with. Switch to attention unit if highways or rivers LOU is low. Section 7, loss functions. As we said, we have 3 options: cross entropy, focal loss, and dice. Let's run cell 7, compare all 3 losses on dummy data. The numbers are different because focal and dice are scaled differently. What matters is which one decrease fastest during training, and that you can only test by trying. Loss function selected, cross entropy loss. Now let's run cell 6B, attention map visualizer.